So in this script, we're gonna introduce Rayleigh fading and Rician fading. Okay, so first, there gonna be some assumption that we have to adhere to. First, we're gonna assume flat fading. So what is flat fading? This happen when we have narrow band transmissions and with the small delay spread. So that means the receiver will see only one coefficients or one path, even though there's multiple paths. Since the transmission has narrow band, the system has very low resolutions. Okay, so we assume flat fading. That means at time index m, the receive symbol, which is y at index m, is equal to the transmitted symbol x at index m multiply with the channel coefficients. So this is when flat fading assumption comes in. You see that it's only one coefficient which contain all the effects of all the paths, right, within one variable. And there's a noise at index m. Okay. So in case of there's no small scale fading or there's no fading, that means this h, this variable h is always equal to 1. Okay. Now, if there's some fading, that means this h will be random, and the distribution of h depending on what kind of fading it is. It could be Rayleigh fading or Rician fadings and other fadings. But here in this clip, we're gonna take a look at these two kind of fading. One is Rayleigh, one is what we call Ricians. Okay. So at the receiver, it will receive a symbol, and then it's gonna pass through uh, what we call match filter. So this filter uh, will be matched with the with the channel. Okay. So remember y is the receive symbol. We're gonna send it through match filter, which is this variable c. So what is this c? So C is equal to H conjugate. Remember H is the channel coefficient, which is a complex number. So we take H conjugate and divided by the magnitude of H. So C has norm 1. So the norm of the match filter is equal to 1. So it doesn't amplify the power of the signal. So the receive symbol pass it to the match filter C, you get the symbol R, which we're gonna use it to detect uh, whatever the transmitter send to the receiver. So remember, C is this multiplied with Y, which is H multiplied with X plus noise. So if we take this and multiply it in, you get H conjugate multiplied with H divided by H, magnitude of H multiplied with X plus H conjugate multiplied with noise symbol divided by H. So you look at this H conjugate multiplied with H. So this is the norm of H square. And you see that one factor can be cancelled out. And this, remember, noise is again, this is random variable. We multiply with H conjugate divided by the magnitude. It doesn't really change the natures of the noise. It's still additive white Gaussian noise, but we're gonna change the variable from N to W. On the other hand, the transmitted signal X now it's gonna multiply by the magnitude of the channel H. So the good thing about the match filter is it match with the channel, and also it uh, rotate the phase of whatever the phase of H is into something that is phase 0, or it's only gonna be the real number. Okay. So X, so if we assume BPSK, then there are two choices: either square root of EB or minus square root of EB. This could represent bit 1 and this could represent bit 0. Okay, so it depends on the quality of the channel. The magnitude could be big or could be small. If it's big, then we say the channel is good. If it's small, close to 0, then we say the channel is bad. Then the detection is this. We take the real part of R. If it's bigger than 0, then we assume that square root of EB has been sent. If the real part of R is less than 0, then the receiver would detect that minus square root of EB has been sent, or, or the detected bit is 0. Okay. Now, if there's error, then the error will occur. Okay. So in case of no fading, that means this absolute values of h is always equal to 1. And the r is equal to 1 multiplied with x plus noise, right? So uh, the only factor that will distort the signal is additive white Gaussian noise. And you have seen this in other class, right? We can analyze the error, right? So if you send square root of b, but receiver detected as minus square root of b, that would be an error, right? So 1 bit error, or vice versa. Bit error rate can be analyzed as such. So it's the Q function of square root of 2EB over N naught. So remember what is EB. This is related to the signal power, right? Remember, if we send bit 1, it's square root of EB. If we send bit 0, it's going to be minus square root of EB. So if EB is large, that means these two values will be farther away from each other, and it's going to take a big noise um, to make an error of it, right? And in 0 over 2, what is in 0? It's gonna be the variance of the noise, or is the noise power. Okay. Now let's take a look at the first kind of fading, which is Rayleigh fading. In terms of Rayleigh fadings, the assumption is this: there's a lot of object in the signal path. So imagine this is the transmitter, this is the receiver. So the signal will go to multiple paths, and then it's gonna reflect uh, to these different objects, and then it's gonna get to the receiver. You see that there's a lot of paths, right? There's many non-line of sight. So all of these are not line of sight, right? So there's no direct path from the transmitter and receiver. So many non-line of sight paths without a strong line of sight. Okay. So this would happen when there's a lot of objects, right, in between, within the signal path. We can model H in this case as complex Gaussian. So C here is the complex normal random variable with zero mean and variance sigma square. We can also assume that sigma is equal to 1, or variance is equal to 1. Sigma square is equal to 1. So what does complex Gaussian means? It means there's a real part and imaginary part. So the real part would be Gaussian with mean zeros, and the variance will be half. So it's sigma squared divided by 2. And then the imaginary part is also Gaussian with mean 0. And the variance is sigma squared over 2. And these two variables are independent of one another. Okay. So in MATLAB, right, you can generate Gaussian random variable with mean 0 and variance 1, right, by using this routine, or this function ran n. Now if you want to generate h, then you would say, okay, you're gonna call ran n, but you're gonna change the variance to sigma square over 2, then you multiply it with the square root, which is sigma divided by square root of 2, plus the imaginary part, right? So I multiply with ran n multiply with sigma divided by square root of 2, right? And then you're gonna get this, which is how you generate h for Rayleigh fading case. Okay. Now if you take a look at the magnitude of this complex Gaussians, you obtain another variable. This is what we call Rayleigh random variable, and this is where the name come from. So h is complex Gaussians. If we take the absolute value, then the magnitude is gonna be random variable as well, and we call that random variable Rayleigh random variable. If you take the magnitude and raise it to power 2, or if you're looking at the norm square, then it's another kind of random variable, which we call exponential random variable. Okay. Now, in terms of another fading that we want to take a look is it's what we call Rayleigh fading. So the difference between Gaussian and Rayleigh is this. So imagine there's transmitter and the receiver. In this case, there's a direct path, there's line of sight path, which is strong between the transmitter and the receiver. Okay, and also there's other non-line of sight path as well. Okay, so we assume that there's very strong line of sight path plus very rich scattering. Scattering means the signal reflected with objects, a lot of objects in signal path, and they're combined at the receiver. In terms of Rayleigh fading, there's this factor K, right, or Rayleigh factor. This is going to indicate how strong the line of sight path is. So what is K? So this number reflects the ratio between the average power of the line of sight path divided by the sum of the power of non-line of sight paths. So this is all the other paths, right? We sum all the power, and the numerator is just the average power of the line of sight path. So if this K is large or big, that means the line of sight path has a very strong power compared to all the other paths. Okay. Now, the way we simulate Rayleigh factor, Rayleigh fading, again, we're gonna simulate this coefficient or random variable h. The way we do it is this, right? There's two terms. The first term is square root of k divided by k plus 1. Remember what is the k? K is Rayleigh factor. So this k is not random, right? So it's some number that fit uh, the transmission surrounding. It could be 10, it could be 2, it could be 5, right? Something fixed. Multiply with sigma, multiply with ej theta. So sigma is the strength of the channel. We can assume that is equal to 1, or sigma squared is equal to 1, just like in Rayleigh fading case. Now the second term, this is going to reflect all the non-line of sight path. And you see that it's also complex Gaussian with zero means and variance sigma square. But then it's weighted by this square root of 1 over k plus 1. Okay, so you can think of the first term as the term that represents the line of sight path. The second term is all the non-line of sight paths. Now this theta, this is a phase, right, which is uniform random variable between 0 and 2 pi. Okay, we can in MATLAB we can generate this by using command rand, R-A-N-D. So there's no n at the end. So that's going to give us uniform random variable between 0 and 1. But we want 0 to 2 pi, so we multiply 2 pi. Okay. Now, if Rayleigh factor is equal to 0 or k is equal to 0, then we get back to Rayleigh fading. How does that work? So let's come back here. So if k is equal to 0, so this is 0 divided by 1, right? So this whole thing will be gone. And this term, so if k is equal to 0, so this is square root of 1 divided by 1, which is 1. So we only have this term. So h is equal to complex Gaussian, which means 0 and variance sigma square. So we go back to Rayleigh fading. So if we set k equal to 0, then it's Rayleigh fading. But if k is large, the larger the k is, it's gonna indicate the stronger the line of sight path is. And this is the end of this clip.